So welcome to Tattoo Universal. This is A-level Caie biology. So I know you're writing the exam this morning. So let's quickly look at enzymes, series 1. Okay, get your writing material. Let's go, guys. I wish you the best in your exam this morning, okay? Look at this question. It says, the enzymes collagenase catalyzes the breakdown of collagen molecules. This enzyme acts by using the induced fit model, okay? So the question says, describe the mode of action of collagenase. So that is induced fit model. So we'll pause the video and try to solve the question. So how does induced fit model act? All right, remember that in induced fit model, the substrate is not complementary to the enzyme's, all right, active site. Okay, so this is the substrate. Is that okay? It's not complementary. Do you get? But what happens is that as the substrate binds to the enzyme active site is flexible. So the enzyme active site molds around the substrate, okay, to allow it to fit in perfectly. So you see, it moves around the substrate. Can you see? This is to form enzyme substrate complex. Okay, so the interaction between the amino acid on the enzyme's active site and the substrate help to form a bond that hydrolyzes the enzyme. Is that okay? Sorry, hydrolyzes the substrate. Do you get? And then that forms product and substrate. It forms product and substrate. So what we have is that the enzyme returns to its original shape. Do you get? Yeah, I'm trying to get the original shape. Yeah. So it returns to its original shape. Yeah. Something like this. So this is gonna be the product. The product. So induced fit complex. Induced fit mechanism. You can see what happens, just to repeat a bit, is that this is substrate is not complementary to the enzyme active site. So as the substrate binds, the enzyme active site is flexible, so it's able to move around the substrate, okay, in order to allow it to bind in more perfectly. You can see it binding more perfectly. That forms ES complex, and when the product is formed, the enzyme returns to its original shape. Okay, so you see, so active site changes the shape. We must mention it. Active site molds around the substrate. That's the same thing. So active site changes to fit substrate more. So active site becomes fully complementary, all right, to collagen. So when changes shape, it becomes fully complementary. Okay, any of these formation of ES, enzyme substrate complex. And you know that enzyme, that's an enzyme, so it lowers the activation energy. So it breaks the peptide bond, okay, because it's still an enzyme. So it breaks the peptide bond of collagen. Collagen is a protein, okay. So active site returns to pre-ES original shape. Yeah. All right, you can see that. So that is what happens. So, but if you are dealing with lock and key, so active site is complementary to the substrate. So substrate binds to it. If you're dealing with lock and key, okay, it doesn't change its shape. But all of this also happens. So when it binds to it, doesn't change shape for lock and key. So our formation of enzyme substrate complex, lower activation energy, breakage of peptide bond. Do you get? Yeah, active site returns to, it doesn't return to its original shape, it still maintains its original shape. Okay, all right, Let's go to the next question. Students investigated the effect of pH on the activity of collagenase extracted from the bacterium Bacillus lentiformis. Okay, at this temperature. Consider temperature then. Okay. The results are shown in Fig 5.2. So this is the result. So this is pH, the effect of pH on the relative activity or percentage of maximum activity. With reference to Fig 5.2, describe and explain the effect of pH, okay, on the activity of collagenase. So I want you to pay attention and try to tackle this question. So, the question says describe and then explain. So describe means show us a trend. You can see that as pH increases, initially, the relative activity of this enzyme collagenase increases. Alright, as pH increases, then it reaches maximum optimum. This is optimum pH, which is 7. Optimum pH is 7. Because that's the pH that gives us the maximum activity, right? So pH 7. So but you notice also that at acidic region and alkaline, this pH alkaline, the relative activity is low. Why are they low at alkaline and acidic region? Because change in pH breaks hydrogen bond and ionic bonds. So when they are broken, what happens is that the active site becomes distorted and less complementary. So less substrate bind to it, and less ES complex is formed. You get it? So look at it, guys. So general description of effect on pH. Example: as pH increases, the activity increases. That's it here. Okay. As pH increases, activity reaches a peak. That's it. Increases and decreases. So it increases after reaching the peak, it decreases. All of this is one mark. They explain. Okay. So partial degeneration in acidic and alkaline condition. So starts to denature as alternative to partial denaturation. To start the denature here and here. Right? Why? You can see that ionizable R group inactive sites are affected. So how are they affected? Hydrogen bonds, ionic bonds break, so active site tertiary structure changes, so substrate collagen no longer fit into the active site or fewer ES complex form. So the guys, this is how it goes. Alright, so look at the next question. Keratin is a structural protein in feathers of birds. Keratin polypeptides are composed of high proportion of cysteine amino acid, which have a sulfur containing R groups. Keratin polypeptides form filaments. The two main types of keratin in feathers are alpha keratin, okay, which consists of many alpha helix, and beta keratin consists of many beta sheet. Okay, that's beta, not G, beta sheet. So protease enzymes hydrolyze proteins. Many proteases are able to hydrolyze more than one type of protein. Okay, how is an enzyme able to hydrolyze more than one type? So just why it is possible for a protease to act on different types of protein. So why is it possible? All right. Pause the video and try to solve the question. Alright, so why is it possible for a protease to act on different types of enzymes? Right, the first reason is because the substrates are similar. Okay, the substrates are similar. It's possible the substrates are similar. That means the substrate have similar shape. They can bind to the active site. Is that okay? Yeah. So the second reason is because the enzyme active site is flexible, so it can change to allow any of the substrates. And of course, the third reason is the enzymes maybe act on the same site, because now look at this. This is keratin polypeptides. So the enzyme possibly breaks the peptide bond between specific amino acids, and they have the same amino acids. So they have the same site where the enzyme, act on. The same amino acid, the same bond. Look at it here. Either that area to be hydrolyzed could between the same amino acid and same acid always hydrolyze or breaks down or act on peptide bonds. Okay, see, based on this, because this is a protein. So suggesting the active site has flexibility for binding similar substrate. Okay, substrate similar shape. Active sites have complementary shapes to all the protein. Alright, see, large enzyme substrate with more than one active site. You get just one mark for all of this. Okay, keratinases are used to degrade the large quantities of waste feathers from chickens and turkeys that are processed in the food. In the product, the feather degradation can be used in animal feed. Okay, same investigation. Okay, some students investigated whether 3 different keratinases, these are keratinases, K12, A22, P3, were suitable as industrial enzymes. These enzymes were extracted from 3 different soil bacteria. Okay, the effect of the temperature and pH on activity of each keratinase were investigated. So let's see. So see the result. So that's temperature. Okay, that's pH. Okay. So the first question we'll look at. Let's go to the first question. It says to upgrade feather waste from industry. It is an advantage to use keratinase that show at least 60% relative activities. Okay. Of course, where temperature and pH can vary widely. Alright, so it shows for each keratinase the working range of temperature and pH where at least 60% relative activity is obtained. So use Fig 2.1 and Fig 2.2 to complete Table 2.1 and use the completed table to name the keratinase that has the widest working range of temperature. Name the keratinase that has, this is the widest working range of pH. So we can complete and name. Alright, so this is a table. So they have given us K12, so pH range with at least 60%. Okay, let's check the pH for K12. Guys, pause the video and come with me. Okay, yeah, that's pH for K12. Where is K12? This. This is 60% for K12. The pH is this. Remember that each box here is 0.1. So K12 is this. If you trace it here, so for K12 it is 6.9. Yeah. Okay. Let's go. This is 60% to 8.4. Okay. So 6.9. That's it. To 8, because we're 60% relative activity. That's what we are working on for K12. Okay. So what we should add there is 6.9. Okay. If you add 6.9, so from what we found out, 6.9, okay, to 8.4. That's the range for K. What we found out here. Okay. So let's check for A2. A22. This is A22. All right. Temperature range for A22. Okay. So let's go back. Yep. So A22. So 60%, let's trace it. A22 is this, okay, X steric. So you trace it, that's this one. So here, okay, that is, remember that each box here is 1, okay. So A22 trace 60, that is where it touches the graph. That's here, that's about 36.5. Trace it again, 30.5 to 57, 36.5 to 57, okay, 36.5 to 57. All right, so that's the range, 36.5 to 57, okay. All right, so the one that has, from this, which one has the highest, pause the video, which one has the highest range of temperature? 4163, okay. I think it should be P3, right? P3 has the highest range of temperature. From 29 to 56 is wider than from 36.5, and then from 41 to 63. So this has the lower, this has the widest range. Which one has the widest, okay, range of, can work within the widest range of pH? Okay, I think it should be this A22 6, that is 3 minus this from this, okay. This is not up to 3, this is not up to 3. So A22 widest pH, right, while P3 is widest temperature, okay. So let's see, yeah, okay. So you can see 36.5 to 57, okay. So widest is P3 for temperature, or for pH is A22. Okay, let's look at the next question, guys. Yes, some detergents contain proteins that to remove stains from clothes. These enzymes have a high relative activities in alkaline conditions. Science reported that K12 and A22 could be suitable for use in detergent industry. With reference to Fig 2.1 and Fig 2.2, discuss the advantages and disadvantages of using K12 and A22 in the detergent industry. Okay. Pause the video. Okay, let's go to that. Reference to this. Okay. Fig, because it says with reference to Fig 2.1 and 2.2. So this is table 2. They don't mention table. Let's go to the Fig. All right. Fig is a graph. Fig 2.1. K12 and A22. Now, if you look at the advantages of using each of them, K12 and A22, what's the advantage of using K12 and A22? So K12, you can say that K12, the advantage is that, look at it, it has higher optimum temperature, okay? So it is more stable, it doesn't denature easily at high temperature. So it removes stains at high temperature because it has highest optimum temperature, and if you can see that it can withstand large range. So this I want to say, and then mention, okay. So you can see that it's still active at 60 degrees Celsius, okay. All right, yeah. So that's K12. But the disadvantage of using K12 is that at low temperature, the activity is below 60. Can you see? So that means it cannot remove stain well enough at below 60. And then you can see that also it only works at high temperature, so that is not cost effective. It's very costly to use it because it requires high temperature, high energy is used. So if you look at A22, see A22, okay, A22 can remove stains well enough at low temperature, you can see. So at 40, okay, now at 30 something is above 60. All right, so you can use lower temperature, it's cheaper, but it's just that at high temperature it's not thermostable, it will denature. That's the temperature. If we come to the pH aspect, so if you check K12, where is that K12? Yeah, so you can see K12. Okay, you can see that you can use it more in alkaline conditions because the optimum pH is 8. 8 is alkaline. Okay, alkaline. Anyway, it has a wide range of pH. We can use it more in alkaline. Okay, but A22, which is this, use it more in acidic conditions. So so if you change acidic condition, it will get denatured. All right. So and if you check also, because we're looking at K22 and K12 and A22. Okay. So the optimum temperature for A22 is slightly alkaline. Okay, is it A22? No, yeah, is neutral. Yeah, neutral. Okay, but it can work in acidic condition. Okay, while K12 works, the acidic pH is the optimum pH, so it works in optimal condition. So these are the things you have to observe and then make. Okay, and of course you see that from this result we have that A22 has the widest range of pH, okay, to work on. So that's an advantage, but it has advantages. Look at it, guys. See the advantage. A22 and K12 act as remove stains at a wide range of temperature. Instead at the range of temperature, so you focus on range of temperature. Use Fig to give activity and stable temperature of good above 60. So goods above 60. Hotter temperatures washes for this. K12 active at low temperature washes. Yeah, this can wash. Okay, can quote the data. Disadvantage: low activity, pore stain removal at 30. That's lower temperature. So you quote exactly. Alright. The data. Disadvantage for pH: greatest activity most effective at this. For A22, at least 60% activity between 75 to 90. So it does quote the range. K12 activity between 7.5 to 80 optimal activity. So this is the range they work better. But disadvantage: use of Fig 2.3 to show decrease in activity at higher pH value. So any wash feature and content. So anyone that decreases at high pH value, that's disadvantage. Have activity at low temperature, so more economic, less energy. Okay. At high temperature, but more costly, need energy. Can wash at high temperature, so can sanitize clothes, can kill insect, pests, can kill pathogens. K12 more thermostable, has high optimal temperature. Only used for K12 at low alkaline. Okay, the alkaline pH is not low, has wider working range. Okay, more tolerant, stable to higher pH. So these are the things we expected to say. All right, let's quickly go. Some polypeptides are translated as part of one long polyprotein chain. After translation, enzymes cut the polyprotein into two separate functioning proteins. Okay, protein is called polyprotein that has been produced within the host cells of actively replicating HIV. The separate proteins are required in replication of the virus. Okay. Alright, look at this. Fig 3.1 shows how the two polypeptide chains of HIV proteins form an enzyme with an activity site enclosed by flaps forming the flap region. Okay, you can see the flap region is the active site. Alright, that's the activity site, enclosed by flaps. So the question goes like this. Let's see. So that's the flap region. The flap region of protease is flexible. So it's flexible. You can see. With reference to Fig 3.1 suggests and explain how the mechanism of action of HIV protease can be described as induced fit. See the induced fit showing up again. Alright. So it is flexible. So that means that the active site is not complementary to the substrate. So as a substrate, which is polyprotein, but I want you to pause the video and try to solve it, right? So as a substrate bind to the active site, the flap region, the active site mold around it to fit in. Okay, so ES complex is formed. It lowers the activation energy. So the interaction formed between the R group on active site here and the substrate can break peptide bond to form products. Okay, now once product is formed, the active site returns to its original shape. You get, look at it. Flap region opens, let substrate enter. Yeah, flap region closes round substrate. You see, in this feed, action involves changing shape. Active site molding around substrate. Okay, flap region changes of active site, or that flap region changes shape because it is active site. Reference to beta fit, this fully complementary when changes shape. Reference to formation of enzyme substrate complex. Okay, yeah, so you can see complementary to shape. Once it changes its shape, they fit in more. So fully fit in. Change of shape to give complementary shape, lowers activation energy, puts strains on the bond to break the bond. Okay, 3 marks. Now see this, Indinavir is one of the therapeutic drugs used in HIV antiretroviral therapy. It is similar to polyprotein, which is substrate of HIV protein. Suggest and explain how Indinavir acts as therapeutic drug. Now guys, try this question. How does it work, guys? Remember that most drugs act as inhibitors. Some of them as competitive, some as non-competitive. Remember, they said it's similar to the substrate. That means it is competitive. So competitive binds to the competitive inhibitors. They have similar shape to the substrate, and then they bind to the active site and blocks the substrate. Okay, so that this polyprotein is not cut. Okay, so that's how Indinavir work. Look at it. Act as competitive inhibitor, binds to active site instead of substrate, prevent entry of binding substrate. So compete with substrate to prevent ES complex formation. See, will be permanent, not reversible causes. So you get, so induces flap region open to bind to active site. So no fewer polyprotein products. That is how they work. You get? Alright, so just to show you something here, guys. So if this is the enzyme here, okay, so and this is the substrate, okay, so the inhibitor in the Indinavir can be like this. So this is substrate, this is inhibitor, this is enzyme. Okay, so competitive has the same, not the same, it has similar shape to the substrate. So it's also complementary to the active site. Right? So it binds and blocks substrate from binding. So when it binds, it blocks substrate from binding, okay? Because it has similar shape with the substrate and it's also complementary to the active site. So 2 marks. Alright, look at this question. Pepsin is an enzyme that hydrolyzes protein. Some students investigated students use pepsin from stomach of a mammal. The activity of pepsin was investigated by placing small quantity of the enzyme with a known concentration of the protein albumin. Fig 2.1 shows the progress of the enzyme catalyzed reaction that was carried out at 20 degrees Celsius. Okay, so as time progresses, you can see concentration of product increases. Okay, so calculate the initial rate of reaction. I want you to calculate the initial rate of reaction. Pause the video. Okay, the initial rate of reaction is the reaction that gives us steepest graph slope. So you can see from here, you can see that from here to here is steep. Okay, and don't forget that rate of reaction is equal to product formed over time. So product formed there is 6 micromole. Time is 10. How do I know? Both of them meet here. Okay, yeah, so that gives us 6 over 10. 6 over 10 is what? Is 0.6. So 0.6 micromole per dm cube per second. Okay, all right, look at it. So it's between 0.6 to 0.8. So if somebody chose another point, all right, somewhere here, maybe here, or from here to here, it could get any of this within this range, but it should be initial rate part that is steep. Okay, look at it. The procedure was repeated to find the effect on the activity of the pepsin using competitive inhibitor at the same temperature. So if you put competitive inhibitor, it's a predict result that will be obtained using competitive inhibitor. So pause the video, predict the result. If you put competitive inhibitor, what happens? Okay, the reaction will be slow. Competitive inhibitor reduces, okay, it competes with the substrate, so the amount of product formed, okay, don't you think it will be reduced? Okay, because we have competitive inhibitor here acting. So look at it, initial rate will be lower. Yeah, takes longer time to reach plateau. Okay, that's a plateau. Yeah, either the final end concentration of product will be the same, yes, but the shape of the graph, ignore the shape of the graph, so it will still reach the plateaus, but it will be slow. The initial rate will be slow. Okay, that's too much. The student extended their investigation by using pepsin from a different species of mammal. The experiments were carried out at 20 degrees Celsius and without a competitive inhibitor, so they'll reduce the temperature. Okay, with reference to fig 2.1, explain the advantage of calculating the initial rate of reaction, okay, in each experiment. So okay, so what is the advantage, guys? Because it is the one that gives us the fastest rate of reaction. Initial rate of reaction gives us the fastest rate of reaction. Okay, why? Because it is the rate of reaction when substrate concentration is still high, and then product concentration does not affect the rate of reaction. Okay, so it's more valid. So we have a lot of substrate molecules available. Do you get? And fewer substrate. Look at it. Allows a valid comparison of the activity. That's why we use initial rate. Initial rate is the fastest. It's calculated over a long period of time than the linear part of the curve. Okay, not limited by substrate concentration, not influenced by increase in product. The product has not increased to interfere with the reaction. The substrate concentration is still high, so the rate of reaction is occurring very fast. Okay, all right. Thank you very much for hanging on. So I wish you the best of luck. This is Shedro from Tattoo Universal. All right, bye.